Okay, so let's start. We will have Mario for the first afternoon session, and he will continue with his course.
Okay, so at the end of this session I will give the details of the project, which is basically to modify embody N2 with substituting the gravitational potential by a Yukawa. So this is a quick review of the questions that you have seen in the course in your PhD, master's degree or bachelor's degree. It's about hydrodynamics, and the method is trying to show how make that the fluids tell us what we want to tell to the research community. Like a Instituto Federal Electoral. So this is a very quick review, and please go to the notes I upload to the Dropbox, which is the SPH report. So this is very quick, and I'm not going to the details, just stopping in some points that I think is very important. So basically the hydrodynamics has in a broad sense two formulations. One is starting from the Boltzmann transport equation and using the invariant, the collisional invariant and conservation theorems. And the other is using the balance equations. And that's it. So using the transport Boltzmann equation is based in, or the Boltzmann transport equation is based in this hypothesis, assuming that we have that the molecules behave as classical particles. Then the classical mechanics is given in terms of the Hamiltonian equations. So this is the concept I gave you before. This is the 6 n-dimensional phase space for the whole system. Each point in this 6 n-dimensional coordinates, each point is the state of the system. And in the case of the mu space, that is the usual form of calling this space in statistical mechanics, is that the system is given by n points in this phase space of individual particle, momentum and coordinates. And we have here the Liouville equation that gives us how the system is evolving in time. And all the n points here is given by an equation like Boltzmann in particular. But Boltzmann is not up to, I know that here we have the Liouville equation for the whole system, but Boltzmann equation cannot be derived using the Liouville equation. So, okay, this is about how the collisional term is coming from, some details, and this is very important concept, the collisional invariant. A collisional invariant is a quantity that is multiplied by the collisional term and integrated in velocities or momentum and give us zero. For example, the mass, or for example, the momenta, or for example, the energy. Those are collisional invariant because each microscopic property is conserved in a collision. So using this concept, we can make this conservation equation in general. So each square bracket part is defined in this way. So if we have the mass, then we have the density. Or if we have then for example, the energy, we will have something similar to the energy field, or the velocity field, and so on and so on. That's the method to in general deduce the Jeans equation or the hydrodynamic equation, for example. This is the typical invariance. So this is just a review. Using this fact, we can deduce the hydrodynamic equation. In particular, we have the terms like are the typical viscosity terms. So, and these are the definition. This is the velocity field, this is the density field, and so on and so on. And this is the kinetic, the kinetic temperature, given in terms of the same average. And this is the flux vector. So the problem, instead of solving the problem, the Boltzmann equation, we can solve these derived equations. So if we assume as an approximation that that a solution to the Boltzmann equation is given in this form, then we can build or construct, using this method, the Euler equation for the hydrodynamic. And if this is a zero order approximation, and if we perturb this approximation, let me see, here it is. I can perturb this approximation, the Maxwellian. I perturb, and then we introduce a parameter that is the relaxation time. So is the time that the perturbation decay to the Maxwellian form. Using this approximation, then we have the Euler equation, the Navier-Stokes equation for the fluid. And all the transport coefficients depends on this parameter, the collisional time. So this is very nice to. It's a way to very nice to understand the concept of the transport equation. Okay, so this is I just jumped all this form to write the fluid equation also using the balance procedure. I'm going to some form to write the hydrodynamic equation. For example, let me see. This is the continuity equation. This is the momentum equation in terms of the integral. And this is the Navier equation in terms of the Lagrangian formulation. And this is the whole equation for the Lagrange form, writing the velocity equation, Navier-Stokes equation. And this is the Eulerian formulation of the same equation. Eulerian and Lagrangian is like putting a telescope and fix in the space a certain angle and let the stars cross. And Lagrangian is put the same telescope and locate a star or an object in the universe and follow the object. This is the Lagrangian. This is a way to understand the Lagrangian and Eulerian formulation. So this is entropy balance, some details. I don't care. You can read it and or whatever. I don't have time to do the whole thing, but I think I write it in the notes more or less in detail. SPH is done in the Lagrangian formulation, so I have to go to this formulation. Okay. So this is Eulerian formulation for the hydrodynamic. The fifth one is the continuous equation with a source, and we have next the Navier-Stokes or the equation for the velocity field with a source also, and the equation for the energy. This is the general equation for the hydrodynamic, and we can write this equation in the Lagrangian formulation. So we have a general vector written in this form. All the fields that describe the fluid are here. I mean the density, the velocities, and the energy. And we can define a kind of Jacobian in this way. And I can write this equation in this form. Okay? And in a compact way, I can write it in this way. So this vector is all with all these components.
What's the fifth coordinate?
Excuse me?
The fifth coordinate, what does it represent? On the definition of the velocity.
B? You,
The first expression, all the way to the right.
the last one
Yeah.
is an energy. This is the density, multiplied by the density, the speed, or the velocity field, and then some similar to the energy, because it's associated to the current. In a compact way, I can write it in this form, and using the chain rule, we can translate and write it in this form. So, okay, so at the end we can write in the Leiden form in this way, and this formulation is like the second law equation at the end. And the SPH formulation is based in this Lagrangian form. Okay, so you can read this in the notes, and go to the concept. This is the concept of the Eulerian and Lagrangian formulation. This is the Eulerian, and this is the Lagrangian formulation. Okay, let me go to the concept of the. This is a review of the same concept before. Okay, so in SPH, what we have to do is to translate all the fields in a grid, for example, and we have in this grid the values of these fields, density, velocities, and energy or entropy, whatever. And we are interested in finding the value here in a point that is not in the grid. So we use an average of the surrounding grid points. In one dimension, or the concept of interpolating or smoothing is that given that we are not trying to know in detail the way that y depends on x, we can just write a smooth proposal. No? For example, in this case, it's a linear fit. And this is more complicated. We just build a random walk in one dimension and try to fit this or to smooth this behavior. The first one is to use moving average, in English, I think. And each, so the curve that follow the behavior of this variable y is averaging subsets of 10 values, for example. You can do with 10 or whatever. So this is a way to smooth the behavior that is following the y variable. Another way is the moving medians or means. I don't remember the name in English, but it's more or less the same. We choose the mean of the elements in the set of data. And we also the exponential smoothing, which is given by this formula. So we have a lot of way to smooth the behavior, the real behavior of the y variable. Another way to understand the smoothing is to think in a 3D surface, and the the altitude or the value of z for this surface, I can write it in the xy plane. In this case, we have a lot of points where I have in the information of this surface. I don't know the surface. I just only know the values of the height of this surface in this finite set of points. And I want to know how high is the surface in this place, and so on and so on. Okay. These are constructed using survey. I don't remember the very details of each of this way of interpolating in 2D in this case, but in surface called minimum curvature, for example. But I try to give you to tell that the smoothing is a very important issue in this numerical scheme, because if you use this scheme for interpolating the values where I don't have information, I have this surface behavior constructed using the interpolation. But if you use this method, I have clearly different interpolation. So the SPS will depend on the kernel, and we have another radial base in this case, and we have the Kriegen. The Kriegen is like a spline, but in 2D in this case, and the natural neighbor, for example. And all these examples show that representing the information where I don't have measurements is dependent on the interpolation method, the particular interpolation method. So that's one of the problems in the SPH. So this is the concept. I have this function g of x prime and can smooth a smooth average of this function that depends on some parameter that in this case is an integral. So I take an interval in one dimension from -8/2 to m/2, surrounding the point I'm interested in, and average the function and give us a smooth version of the function. This is another way to see the concept of smoothing. So again, the hydrodynamic, the smooth particle hydrodynamic base in that I have information only in a finite set of points in the space, and we are interested in finding information in another set, in another point. Okay, just going more in details and moving forward to the SPH formulation. I have this the definition for the SPH. So I have a field, and this field depends on position and time, and use a kernel to smooth this field. And this kernel have to satisfy these two conditions. The total integral, it means if I have 1 here for A, so the integral of the kernel should be 1. And the behavior when h goes to 0 should be Dirac delta. Then another important thing is that in the hydrodynamic equation we have that the fields normally are, we operate with the nabla, gradient, divergence or rotational, and the important thing is that this operator goes, in this case, to be written in this, and according to the definition of the smoothing version of A, but using the integration by parts, we can translate this operator to the kernel. So this is the most important thing. So when I write the hydrodynamic equations, all the derivatives for the quantity goes to the kernel. So the kernel is tabulated at the beginning of the simulation, and I also write the derivatives for the kernel. They are tabulated, so I can establish a very fast method. And we have this property, we have also this property. Okay, so these are again the hydrodynamic equation in this form, in the conserved form. And then I have to show that the derivative of this field, remember that this is the density, the velocity field, and the energy field. And we have that using integration by parts, that the derivative can commute with the averaging operation. So this equation translates to this form, and that's it. At the end, we have this form, the Newtonian second law. The sources of the equations and the derivatives of the associated equation, the associated quantities. Okay, so in detail, in general, we have, for example, that instead of using, for example, the continuity equation, it's better to follow the particle, and each particle is a dot that I schematically put here. So in SPH, we think that these are particles, and we have a law to follow the motion of this particle. But each particle has not only momentum, position, and velocity. It has internal energy, temperature, pressure, and so on and so on. So it's a volume element. Okay, and each of these particles have this equation of motion. And that's it. So I have just to write down for each of the equation and translate to this smooth version. And for autogravitating system, I have to include the Poisson equation. Then that's it. Okay. So, but these are discrete, so the integral should be translated to this. And in general, so a field have to be written in this way. And we need another step, how to write this average of the density number of particles. But that is very easy, because this is the definition, and at the end we have that the average of this is the density divided by the mass. So this expression can be translated as in this way. So the average in a position of a given particle, for example, AY will be written in terms of the sum of the values of the same quantity in the neighbor particles. How many neighbors are needed to represent quite well this quantity? Well, this is a numerical issue. Then, in terms of the summatory instead of integral, the gradient can be written in this form, and so on and so on. In this way, using the mass and the density. Divergence, for example, can be written in this way. And there is some details that we have to take into account. For example, this is the expression for the velocity, the equation of the velocity of a particle, but if, and the gradient of the pressure is this one. However, this expression does not concern linear momentum and angular momentum, but we can use this relationship from vector analysis, and then instead of writing in this way, we can write it in this way. In this symmetrized way, we have conservation. So there are some details that we have to take into account. But the main point is that the derivatives, gradients, and so on are going to the kernel, and the kernel can be written from the beginning in a table. All the derivatives are written in a table, and they are at hand. So it's quite fast. It's a very quite fast method. For the energy is something similar, and so on. Okay. How can I find the neighbors of a given particle? I have to ask, given a certain radio for a particle, how many particles are in this region that can be considered as a neighbors to do this sum, for example, or the one before. How many neighbors I have to use? So I have to fix the number as a parameter, as a numerical parameter, but I have to ask, given a particle, which set of particles are in this volume. So I have to do a loop as before, which is n square complexity. So instead of doing that, I use the tree concept. I have been classified for computing the gravitational force. I use again to find efficiently as order n. No, in fact this is more quite fast. So instead of asking, given this particle, how many are surrounding, I just follow the tree code and ask what are the cells that are neighboring to this one. So this is very, very quite fast. Another point is that the boundaries, we don't have grids, and so this is it's a method very useful for astrophysics. Okay. Any question? Okay, but I have a question. Okay, the project, the first project depends on, I put it in the Dropbox. It's installed all this, as I told you, and then modify this code instead of using the standard potential that it has the Yukawa force. That's the problem. Okay, so what is the structure? Again, the point is you have to go to the sources, go to the gravitational. This is the so let me clean this code. Okay, so these are all the codes that you have to see inside. So how many parameters does Yukawa have? It's the length and the intensity, right? So the intensity is like the gravitational constant. So you may use this just to include the parameters of the Yukawa. But the main, you don't have to see the main, of course. There is nothing to modify here.
Where's that file?
Huh?
Where is that file?
Sources. It belongs to the gravitational set. Is the n-body n2. And then these are all the sources that you need or look into. So this is a data structure. The first file to see is this one, because here is the interaction. So this is the main routine to see and to think how to modify in order to take into account the Yukawa potential. But the Yukawa potential you have to translate instead of, the potential is exponential minus r over lambda over r. But the force is different. And the particles move not with the potential, moves with the force. So let us see where maybe no. Let me see if we have here. No. Maybe here. A Yukawa potential comes from, for example, scalar tensor theory. Here it is. So this is the force for the standard potential. If you introduce a Yukawa force, then all the modification is in this function, which is in this form. We have alpha and lambda as a parameters. So you have to include in the n-body code this modification. So here is just this acceleration is it is in this factor mr3i, because that is 1 over r squared, for example. And instead of having this, we have to have this term plus the Yukawa contribution with 2 parameters. And that's it. Any questions?
Yes.
Yeah.
Suppose that we done the modification now and we need to compile the project. Need some special steps to do this, or are like the instruction of the another pattern?
No, you have to go inside and make the program. Also, make the programming changes. Okay.
So
You already did.
yeah.
Okay.
How I compile the changes now?
Okay. So the video, for example, the video will be different because it's not one of R. So you run the same globular cluster, the Plummer model, with the standard gravitation and with Yukawa. Okay? And the result must be different because you have now a Yukawa contribution. And the video will be different. Any other question? Gustavo, how much time do I have? 20. Okay. So any other question? Okay. So is clearly enough the project? Mm-hmm.
I'll ask you for the specifics so I can upload them in a second.
Okay. Another details. Remember, all the parameters, all new parameters are introduced in here. Alpha and lambda, which is the intensity of the Yukawa and the range of the Yukawa, should be included as an input for the code. So these parameters should be here in the command line data structure. Not in global, for example. Okay. Once you register here these two parameters, you have to go here to the start run. And here there are a lot of things that this code do to process the input. For example, here, this instruction, this one. This instruction, what it does is to read the command line option EPS, get its value and assign the value to the corresponding variable. So in the same way, you have to just modify here, for example, here, and put alpha, okay. Alpha can be positive, negative, and whatever, right? So we have, and here, we don't have to check parameter for alpha because it's more or less well behaved, right? Here I read from the parameter line for a parameter file. So alpha, and where is another EPS, because I follow where the EPS parameter is process. So this is alpha. Okay. So I register the alpha new parameter in parameter processing or command line processing. Okay, I think. Then I should remember that I have to include here. So I look for epsilon parameter is here. I just copy the line. Why? What is the default value could be? Well, there is no Yukawa contribution. And we have force, smoothing length, so this have to change. Yukawa intensity. And just compile. I don't know what it's going to do. Error. So alpha, let me see. Global, here, is missing. Where is it? Epsilon. I'm just following where is the epsilon parameter, because it's quite similar to that in the type, not in the behavior. And that's it. So you just run and plot body n2 minus health and give us the alpha parameter. So this is the way I include a new parameter, but now I have to program using the parameter. And for alpha is the same, and then you have to program. So we already have functioning alpha parameter. Okay. So the project is more or less clear. And then you have to test this new or modified code. So you have to compare without Yukawa and with the Yukawa included, and how both of these models compare, and how the virial is modified. Okay. Okay, just to finish, I would like to go to some details of the programming structure. Here. I think it's here. Okay, so I include well, more files, but let me see the Dropbox, or maybe the here. So let me show you how works this Nginx generator for initial conditions in the cosmology and run some tests. So I am assuming that you expand this package like was done before. I think is like this one, right? But instead of this embody tree, you use Nginx initial condition package. This one, Nginx. So just in package, go to the NAGBO default and make the So we have the binary here, and also do some similar to other gadget programs or code. For example, okay, this one and this one. Lambda CDM. the same for another. GDT. Okay, now P. So, okay. So these two codes, the SPH and lambda CDM is gadget codes for doing hydrodynamic simulations, including gravity, using the SPH method, but it's serial, so you can follow very clearly the way it was programmed gadget, without NPH and that stuff. And lambda CDM is also serial, erasing all the MPA instruction in order that you can see how is programmed the lambda CDM, or well, similar to lambda CDM. Okay. And here is gadget 2, but just the with the 3N method, 3PM method, and without the 3PN method. But in this case, these two versions of gadget are parallel. Then the way of installing is the same. And lambda CDM, and for the other ones is quite special, because you know in gadget we have three cases. We have the gas sphere, the lambda CDM and gas cosmology. We have the cluster, and we have the galaxy collision. So if I want to install this version, just like every other blackbody code, I will do it in this way. But I have an error, because I have to tell to the making process that I have a interest in some particular simulation. So the first one could be, for example, gas sphere. Okay, but given that I can make in installing all the cases in gadget, and one code may use the 3PN method and other cannot or not does not use the 3PN method, then I have to do it this way. Before installing the code, I have to clean in order to erase, because in the previous installation can be invoked using the 3PN method, for example. So I clean the installation and then install the case.
Is that that's explained in the...
Yes, in the Mac OS installation. Yeah, it's in. Let me show you. Gadget files, and then so both steps are necessary. So clean the installation with the gas sphere name, for example, or galaxy, whatever, and then install the version. Okay, so that's it. For example, I have the clean for lambda CDM gas, and then install the lambda CDM version. And do the same, for example, for then without the 3pm method, clean and then install. So in the binary directory I have all these kind of versions. So they are available now. So let us use it using this generator of initial condition. We have first to make the initial condition using the Cheldovich approximation. The more important thing in terms of the number of particles is here. The tail factor is 4 in the original version of the engine, the one that you download from the Springer home web page. It has 8 value, but it's very big number of particles. If you use 5, you get something like 500,000 particles. If you use 4, it's going. It's like n equal to 60,000 particles. So in terms of time, it's better to use this one. And to do it, just follow this instruction. Another thing. Where are the files created? So this is the directory where you are installing the files. So it's just run this one. Okay. Doesn't work. Okay. And generate the files. This one. And then running. Yes. Okay, let me just run the. So here the important thing is to modify the parameters input for the gadget. Where are the condition files? Are the files that I make with Nginx that are here, and the output will be in this directory, and the cosmology will be the same as the initial condition was built. You can check this value in the parameter for the Nginx. So just see what is done. MPI run minus MP for processor gadget GDT. The fastest one in case of cosmology is the with 3 PM using the lambda CDM gas parameter file. The output is here. Because I'm in the third. Okay, this is working. And that's it. Should be here, but I haven't seen, but it's clearly here. That's the guided for processor running. So you can try by yourself different cosmologies. For example, use omega matter codominated universe, put in here 1, 0 the cosmological constant, and so on, or all baryons, or all cosmological constant, and so on. But the same modification should be done in the running for in the parameter file for running the simulation. Any question? And the last thing is to see the running this is using the guided viewer, and all the snaps that were written. This is a set equal to 50, I think. No, 10 or something like that. In fact, it's here. This is the structure that is comes out from this simulation at the present epoch. The next thing is to find the correlation function and power spectra and so on. Okay, just to finish, because this is my last. So all the lectures will be uploaded in the web page. Where I am. Okay, lectures. So the last lecture is the end, of course. So, okay, the idea of developing this codes is just to share with the community, and we have two type of consideration, that the software be free or just the binary free. And if the software is free, okay, it's good. But normally the people that develop numerical codes do it in a hard way. So using pointer and such thing, and designing the structure of data very difficult to understand. The routine is also very difficult to understand. So the next step is that the software be free and that the knowledge that that we use to build the software be free. And that's why I am trying to do it in this way. It means that it's the binary time step, for example. The code is self-explaining, so the knowledge is free. The software is free and the knowledge is free. So you can very easily modify the code. So at this point I stop, and thank you for your attention.
So basically what we're going to do now is all the speakers will come up front and tell you exactly what the projects will be with more detail, and also there are a few students who volunteered to prepare a GitHub page so that all the stuff will be there and easier access. So I guess the next speakers can just get on the stage.